Afternoon, everyone. Once again, I welcome you all to the live interaction session 5 for the NPTEL course Computational Fluid Dynamics. The course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras, while myself, Ankara Karthika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, I'll be handling this live session. For your information, this video is being recorded so that we can use it for later purpose. So this session has been happening every Saturday from 3 p.m. to 5 p.m. So now we'll start the session. So course layout, this computational fluid dynamics CFD course is a 12 weeks course. So basically like we have almost covered the basic requirements for understanding CFD in this 12 weeks. So initially in week 1, we saw the introduction to the calculation of flow in a rectangular duct, and in week 2 it was about calculation of fully developed flow in a triangular duct, and week 3 it is derivation of equations governing fluid flow. Week 4 it is about equations for incompressible flow and boundary conditions. Week 5 and week 6 it is about basic concepts of CFD, basically finite difference approximations, and they criteria like consistency, stability, and convergence, which we need to know to have a complete knowledge while solving those equations, because the ultimate aim is to get the solution. For that we need it to be, the system need to be consistent, stability, and convergence. And in for future weeks we'll be seeing about the solution of Navier-Stokes equations for compressible flows and incompressible flows, and the mathematical solutions for these linear algebraic equations, basic methods as well as advanced methods. And finally in week 11 it is about basics of finite volume method, and finally it is about turbulent flows. So basically the NPTEL course covers the or NPTEL course provides the lectures for all these problem solving sessions are just to help you and give you an idea about solving the assignment problems, as well as like it would be helping you in appearing for the exams as well, because since we are solving all the answers you would be having an idea. And till now we have seen the flow in rectangular duct and triangular duct, and equations governing equations for fluid flow, and equations for incompressible flow and boundary conditions, everything we have seen. So now we are going to week 5. Here we will be having basic and practice problems from week 5 and some solved problems from week 4. So now we will start with week 4 assignment problems. So here we have been provided with the case. This is similar to what we saw in last class. So if you remember in last class, last Saturday, we have seen a basic problem or a reaction happening inside a reactor. So in that particular thing, we have seen how CFD can be applied in that case, and how the solutions we were able to frame, like in terms of governing equations or in terms of boundary conditions, whatever we saw last class. So this week is an extension to that with a new case. So the case is involving this particular geometry, and we will see what is given. So it is given that a catalytic flow reactor having dimensions length into W into H, such that length is very much greater than W and W is greater than H. Gaseous mixture of carbon monoxide and water enters the reactor through plane A and leaves through plane D. Catalyst is coated on the bottom wall between planes B and C, which are at distances of 0.5 and 0.75 times L from the inlet. The reactor is preheated or cooled through the top and bottom walls over the distance between planes A and B. So first we need to identify what is given in this problem. Like first thing, it is a catalytic flow reactor and its dimension is this, such that length is the greatest of all and H is the lowest of all. And what is the reactant mixture we are sending? We are sending CO and H2O, and it goes through A and leaves through D. Catalyst is coated on the bottom wall between planes B and C, which are at a distance of 0.5 and 0.75 times L from the inlet. So we'll first modify this diagram or make markings in this diagram so that we can get a clear idea of what is given in the system. So this is given, so it is, as you can see, it is x, y, and this is z. So from this we can see that length into width into height. So this particular side is the length of the reactor, which is the largest of all, and this particular side is the height. So height is the smallest of all, and here in terms of this we have width, that is in between length and the height. So what mixture we are sending? We are passing the gaseous mixture through this plane. This is the inlet plane. Plane A is the inlet plane and plane D is the outlet plane. So this gas mixture of carbon monoxide and steam, it is passing through this particular plane and it is leaving through that. In between reaction is happening and it is producing carbon dioxide and hydrogen. So that we can see in the next slide. So catalyst is coated on the bottom wall between planes B and C. So as you can see, this red color portion is there which is coated with the catalyst coating. Okay. Between planes B and C which are at a distance. So B plane is at 0.5 times L and plane C is at 0.75 times L. So by the time it is almost reaching and crossing C and D, we can say that some amount of uniform flow can be achieved, and reactor is preheated or cooled, like depending on the reactant temperature it is either preheated or cooled through the top and bottom walls over the planes A and B. So planes A and B is there na, from the top and bottom wall, this top wall and bottom wall, there is a heater or cooler, so which is heating or cooling up the reactants depending on the requirement. So we'll have, what we need is we need to solve for the flow in a reactor in which the following water gas shift reaction is taking place. So carbon monoxide plus water is giving carbon dioxide plus hydrogen. So the reaction here we are given the reaction conditions. So the reaction is mildly exothermic and it is to be carried out in a targeted temperature range based on the desired output composition. So this is an exothermic reaction. So this will be giving out heat. So there is a requirement for maintaining a particular temperature so that the optimum products would be formed. Amount of concentration of the products would be formed. So all the species are in gas phase, but the reaction is catalytic. All the species are in gas phase, but the catalyst reaction is catalytic. In the reactor shown in figure 1, the catalyst is coated on the bottom wall between planes B and C, which are at a distance of 0.5 and 0.75 L, which we saw in the last slide itself, and respectively. We wish to use the length of the traverse between plane A and B for preheating or even cooling if the reactants are at too high temperature to begin with. So what they have given is that if the entering reactants are at a very high temperature, they need to be cooled, or if it is at a low temperature, we need to be heating. So since it is a very basic problem, we are given that conditions. Like it can be heated, preheated or cooled depending on the requirements. We need to find out how much conversion takes place, how much of the carbon monoxide coming through the inlet gas converted to carbon dioxide and to the production of hydrogen. We want to find this out using CFD simulations. Assuming steady laminar flow, answer the following questions. So basically, this is the reactor setup. So we have a fluid inlet, gas inlet of carbon monoxide and steam, which is passing through the plane A and it is leaving through plane D. In between that we have planes B and C, which is coated with a catalyst, so that reaction is taking place and carbon dioxide and hydrogen is getting formed, which should also leave through the plane D. So plane B is at a distance of 0.5 times L at midpoint of a plane inlet and outlet planes, and plane C is at the midpoint of planes B and D. So the reactor is preheated or it can be cooled if the reactant temperature is too high. So and it is given that the reaction is exothermic. So based on this, if our objective is to see how much CO is converted to CO2, and if we can do this, like the we need to find out the conversion, like not exactly the conversion rate or something, but we need to know if we can use the CFD tool to estimate this, and what would be the governing equations and what would be the boundary conditions that we can be using. Those are the questions that would be coming up in the next slides. So, and one more thing it is given us, we are assuming a steady laminar flow and we need to answer the following questions. So, we will go to the questions. In question 1, yeah, before going to questions, we'll just see the governing equations first so that it would be clear to us uh, what are the equations we would be solving. In from by now we know clearly if we are dealing with only fluid flow, what would be the governing equations we would be solving. We will be solving for continuity equations and momentum conservation equations. And if since here it is a reaction, we are one more equations we are solving is species balance equations, because we need to know how much of carbon dioxide, carbon monoxide or any other species is in the inlet as well as in the outlet. So for that we need to solve the species balance equations, and here we are dealing with temperature change as well because of the reaction conditions, and it is again given it as an exothermic reaction. So we need to solve for energy balance equation as well. So we'll see that continuity equations. Continuity equation is given by dou rho by dou t plus del dot rho u is equal to 0. So remember that these equations are basically in the vector form. So we are not writing separately for the xyz. So it is dou rho by dou t plus del dot rho u is equal to 0. That is the continuity equations which we would be using. And next is the momentum conservation equations. It is given by dou u by dou t plus del dot uu is equal to nu del dot del u plus g minus 1 by rho del p. So this is the momentum change in the system, and this are the like different forces acting which should be affecting the momentum balance inside in the systems. For example, this is the pressure gradient force, and this is the gravitational force, and this is a viscous force, and like these are the change due to time, because of time how much it is changing, like flow over time. And this is energy conservation equation. It is given by dou t by dou t plus del dot ut is equal to k by rho cp and into del dot del t plus mu by rho cp 5v plus qr by rho cp. And species conservation, it is given by dou rho yi by dou t plus del dot rho u yi is equal to del dot gamma del yi plus si. Y is nothing but the concentration of that particular species inside the system, like ith species, or in terms of mole fraction, I mean mass fraction, I guess. So now we'll go to question 1. In question 1, it is given that how many mass conservation equations do we need to solve? Only one for carbon monoxide, only those for carbon monoxide and carbon dioxide. Option C, any 3 species conservation equations and mixture continuity equation. Option D, none of the above. So how many mass conservation equations do we need to solve? Like we'll be having, how many species we are having? We are in the reactant side we are having carbon monoxide plus steam giving carbon dioxide and hydrogen. So on the whole we have 4 species in the system and we have 1 continuity equations. So if there are 4 species balance equations, together if we put all, it would be leading to continuity equations. So there is no, like, we need to subtract 1 from the species conservation equation and solve in the continuity equations. So the number of species conservation equations would be 4 minus 1, because here again we are dealing with whole system as a continuity equations. So 4 minus 1, 3, and this one would be 1. 3, any 3 species conservation equation and one mixture continuity equation. So option C is the right answer. Answer is option C. So how it is? Number of species is 4 because carbon monoxide, carbon dioxide, H2O and H2. So we have 4 species in this particular reaction, and continuity equation is 1. So we are subtracting 4 species conservation equation. The number of species conservation equation that we need to solve in this particular problem is ns minus 1. Here it is 4 minus 1, 3. So total number of equation is ns, that is 4 minus 1, 3, 3 plus 1 again 4. So we will go to question 2. In question 2, it is asked that which of the following statements is true about the chemical reaction? Option A, the rate of reaction needs to be specified. The stoichiometric coefficients of the reaction are sufficient to calculation the reaction rate. Option C, rate of reaction need not be specified as it can be calculated assuming thermal equilibrium. Option D, kinetic parameters of the reaction rate needs to be specified. Option D is the right answer, I think. Yeah. Because what for when we are solving about chemical reaction inside the system, we need to have an idea about the kinetics of the reaction. Kinetics of the reaction include stoichiometric coefficients of the reaction, reaction equation, in the reaction equation, and the order of reaction, that is first order, second order, whatever, and the constants in the rate equation. So rate constants. So it is option D. That is, we need to know kinetic parameter of the reaction rate needs to be specified. So this is the true statement about the chemical reaction. Like, it is not stoichiometric coefficients of the reaction are not sufficient. We need to know that as well. Like, it is one of the thing, but it is not sufficient to calculate the reaction rate. Here we are dealing with the chemical reaction. So what the things is required on the whole is that kinetic parameters of the reaction rate associated with that particular reaction needs to be known to have a complete knowledge on the system. We will go to question 3. In question 3, it is given that in figure 1, the thermal boundary condition over the top wall between planes A and B can be temperature specified. Statement 1, temperature specified. Statement 2, heat flux specified. Statement 3, heat transfer coefficient specified. Option A, 1 and 2. Option B, 2 and 3. Option C, 1 and 3. Option D, 1, 2 and 3. So actually we have two types of boundary conditions. The first one is we can either specify the value of the dependent variable at that point, that is known as Dirichlet boundary condition. Second is Newman boundary condition. Newman boundary condition is that we specify the derivative of that particular variable, value for the derivative of that particular variable at that point. So it can be either direct value, or we can specify value of the variable, or we can specify the value of the derivative. So it is either temperature specified or heat flux specified, because if the figure 1, we can see that it is between planes A and B. It was mentioned that the top wall and the bottom wall are heated or cooled, like depending. So we need to give some boundary conditions for that. What boundary conditions can we give is the question. So temperature, it can be like, since it is a heating problem, we can't give heat transfer coefficient because it would be like not suitable for this, because that would be specifying for that particular material also. And but we need to know that like how much heat is passed from this end or how much it is cooled. So for that we need to know either the temperature or we can specify the heat flux. So option A, that is 1 and 2, is the right answer. Option A is the right answer because we can specify either the temperature or we can specify the heat flux, but we cannot use the heat transfer coefficient. We'll go to question 4. In question 4, in figure 1, if the reaction rate is very high, the boundary condition for carbon monoxide species conservation equation at the bottom of the reactor between planes B and C is option A. First one, concentration is equal to 0. Second one, concentration gradient is equal to 0. Third one, concentration gradient is equal to constant. Okay. So what is given if the reaction rate is very high? So reactants are carbon monoxide. What is given basically? Okay. Carbon monoxide and H2O are the reactants. So this is giving products. What does it mean if they are saying that here we have A plane, like we'll keep it like this so for our understanding, A plane, B plane, C plane and D plane. So here catalyst is coated. And if the reaction rate is very high, the boundary condition for the species carbon monoxide species conservation equation at the bottom of the reactor between planes B and C. So between here at the bottom, like since it is like this, what is the bottom boundary condition? So what is that? Here at that point catalyst is coated between those two planes, and if it is carbon monoxide, what can we say? If the reaction rate is very high, we can say that carbon monoxide can be utilized completely. So the concentration we can put it as 0 if the reaction rate is very high at the bottom. So that is concentration is equal to 0 is the right answer. Concentration gradient is equal to 0, meaning like there is no change, and concentration gradient is equal to constant, not equal to 0. Like there is some change but it is a constant one. So these three are the options given, but since it is mentioned that reaction rate is very high, so reaction rate is very high, so what can be the boundary condition? If the reaction rate is very high, the chances of the carbon monoxide depletion is there. So at the bottom of the reactor there is catalyst again, like so catalyst is coated on the bottom wall between planes B and C. So the catalyst coating is there as well, so the chances of carbon monoxide on that surface is very less. So we will see the options. Option A, that is 1. Option B, it is 2. Option C, it is 3. Option D, it is 4. Sorry, option D, boundary condition is not required. So option A is the right answer. That is 1 is the right answer. Option A is the right answer because we are saying that carbon monoxide are between planes B and C at the bottom of the reactor. At the bottom of the reactor, the first thing is it is coated with the catalyst. So if the reaction is very high, the conversion from carbon monoxide to carbon dioxide would be very high. So chances of carbon monoxide reaching is like it would be 0, and also it is coated with the catalyst. So it is concentration of CO is 0 at the bottom of the reactor is what we give as the boundary condition for the species conservation equation. That is carbon monoxide species conservation equation. So option A is the right answer. We'll go to question 5. Question 5, it is given that which of the following statements is true about the expected temperature variation along the center line of the reactor if the reactant enters at low temperature than the target temperature? What is given is that which of the following statements is true about the expected temperature variation along the center line of the reactor if the reactants enter at a lower temperature than the targeted temperature? Temperature decreases monotonically in the flow direction. And option B, temperature increases monotonically in the flow direction. Option C, it is temperature increases in the first half and then decreases. Temperature increases up to plane C and then remains constant. So basically, where is that? Like this is the reactor. So we are tilting a reactor for our convenience. So this is A plane and this is plane D. Like here it is entering and here it is leaving, and in between we have planes B and C. So it is not properly made, so just adjust with that. Which of the following statements is true about the expected temperature variation along the center line of the reactor? So what is the temperature variation along that line if the reactants enter at lower temperature than the targeted temperature. So what is given? Reactants are entering at a lower temperature than the targeted temperature. So this is mentioned that it is an exothermic reaction. So temperature would be given out during the reaction. So if already the temperature is lower than the targeted temperature, so what happens is that between B and C only the reaction takes place, because between B and C only catalyst is present. Therefore, the conversion from carbon monoxide to carbon dioxide happens between that zone B and C. So after that, reaction will not be taking place. So while the reaction is happening, the temperature would be increasing. So if before that it is entering at a lower temperature, so during in the plane between B and C, it is exothermic reaction, so it is giving out a heat and the temperature is rising, and after C it remains constant. So first option is that it decreases monotonically in the flow direction. It is false, because it is an exothermic reaction. There is no chance for the decrease part, and it increases monotonically in the flow direction. This is can be true for some half, because after C it is not increasing further, because along the center line of the reactor, meaning from the start to the end. So since at the inlet itself it is entering at a lower temperature than the targeted temperature, it is increasing in the temperature from planes A and B. So between A and B, again we are providing heat. It was mentioned that it can be preheated or cooled depending on the requirement. So since the reactant is entering at a lower temperature than the targeted temperature, between planes A and B, there is a heater according to this context. So there is a heater and it is increasing the temperature. After B and C, it is further increased because of the exothermic reaction, and after C it remains constant. So temperature increases in the first half and then decreases. So the first half of the plane, if you remember, the plane B is at a midpoint. So the first half is still plane B. After plane B, it should be decreasing if it is an endothermic reaction, but here it is an exothermic reaction. So it is still increasing till plane C. Option D, temperature increases up to plane C and then remains constant. So it is increasing and then remains constant after C, because it is leaving out the reactor within some distance. So now I answer is option D, because from what is the reason? We have a temperature variation along the center line of the reactor, and it is given that reactants are entering at a lower temperature than the targeted temperature. So between planes A and B there is a heater. Preheater is there. So because of that, initially temperature is increasing up to the first half. And from planes B and C, if it had been decreasing, we could have gone with option C. Whereas the reality is it is an exothermic reaction. So between planes B and C, again the temperature is increasing, and after plane C there is no reaction, so it is constant. So answer is option D. I hope it is clear. Now we will go to question 6. In question 6, it is mentioned that viscous dissipation term that appears in energy conservation equation is absent in option A, inviscid flows, option B, incompressible flows, option C, non-Newtonian flows, option D, inflows with shocks. So viscous dissipation term that appears in energy conservation equation is absent in like viscous dissipation, meaning like because of the viscous force, if there is an energy loss that is happening inside the system, that would be absent in which of the following systems? So option A, it is given inviscid flows. Inviscid flows is an ideal system, like where it would be viscosity is 0. If viscosity is 0, we can say that there is no viscous energy loss. So option A is the right answer. If we further look at the further at the other options, it is given incompressible flows. It should be included in incompressible flows, and non-Newtonian fluid flows, there are viscosity effects, and therefore viscous dissipation term would actually come, because non-Newtonian fluids the viscosity is varying, but it doesn't mean that viscous dissipation effect is absent. And option D, inflows with shocks, again here viscous dissipation term needs to be appeared. So answer is option A. So how if we look at it? So inviscid flow, it is given by viscous shear and non. What is inviscid flow? Invisible flows are nothing but where viscous shear and normal stresses are negligible. So those systems we call it as invisible flows. So like in real heat transfer problems, like heat fluxes are strong and temperature variations would be associated with the flow, like concentration of like in, if we are considering the invisible flows and contribution of viscous dissipation is small and it is therefore neglected in these systems. But if the system is having highly viscous fluid like glycerol and petroleum crude oil, imagine the viscous dissipation that would be there because of the work done by the viscous force. Therefore it would be there in those systems. There we cannot neglect that uh, viscous dissipation effect. So for highly invisible flows, nothing but viscous shear and normal stresses are negligible. So in real heat transfer problems, heat fluxes are strong, temperature variation associated with the flow. Contribution of viscous dissipation energy is small and neglected. But for highly viscous fluid like glycerol, petroleum crude oil, the viscous dissipation of energy is considered. So, like this is the energy balance equations. If you look at the mixture energy balance equation, energy conservation equation, rho Cp dou T by dou T plus rho Cp del dot Ut is equal to K del square T plus mu phi V. So, why we cannot neglect the effect of viscosity in the highly viscous fluid? Consider mixing of a highly viscous fluid using an impeller. So the viscosity would generate a sufficient amount of local dissipation. Like if the fluid is very like cornstarch, like last time itself we saw, one fluid is a cornstarch fluid. Like remember mixing it using an impeller. Like its shear stress is not, it would be shear thickening fluid actually. So viscosity would generate a sufficient amount of local dissipation, and therefore the local increase in temperature would be there, and that local increase in temperature would have a large consequent may have a consequent large change in the viscosity, which would then be coming into the momentum equation, and that could change the velocity field. So everything is interlinked actually. So highly viscous fluid, when it is there, so because of the high viscosity, those fluid would generate a high amount of local dissipation, and because of that increase in temperature would be there locally, and this thing would again affect the viscosity. This viscosity would be coming back in the momentum equation, and that could change the velocity field. So but for light viscosity fluids, liquids and gases, viscosity term could be neglected because it's like water and all. When like very, if not water or any light viscous fluids, when we are mixing, like the viscous dissipation would be very low, so that in those cases we can neglect the viscosity term in the energy balance equation. Viscous term, dissipation term that appears in energy conservation equation is therefore absent in inviscid flows. Incompressible flows like other fluids will be considering the effects. So but in inviscid fluids we can neglect the effect. So actually I cannot, like light viscosity fluids, liquids and gases, the viscosity term could be neglected. Light viscosity fluids, like this can be removed actually. It will be pretty confusing. So we'll go to question 7. In question 7, it is mentioned that which of the following is already included in the energy conservation equation that we solved along with Navier-Stokes equations for flows with heat transfer and therefore do not require further modeling. So which of the following is already included in the energy equation that we solved along with Navier-Stokes equation for flows with heat transfer and therefore do not require further modeling. So what is asked is that which, like, uh, for heat transfer problem, we solve energy balance equation along with the Navier-Stokes equation. So what terms are already included in that and which do not require further modeling? So option A, option 1, conductive heat transfer, option 2, convective heat transfer, option 3, radiative heat transfer. So actually, radiative heat transfer requires further modeling. Apart from that, the conductive heat transfer and convective heat transfer are already included. Which of the following is already included in the energy equation that we solve along with the Navier-Stokes equations? So when we are dealing with the heat transfer problems, we can use the conduction heat transfer and convective heat transfer are already included. And radiative heat transfer needs further thing. So option A 1 only, option B 1 and 2 only, option C 1, 2 and 3, option D none of the above. So answer is option B 1 and 2 only, because if you look at the energy balance equation, we are included the conduction part as well and convective flow, like how the temperature is changing because of the fluid flow behavior, that is included in the U and T terms are included as well. So convective heat transfer in terms of the temperature change due to fluid flow is also included, and conduction heat transfer effects are also included, but radiative heat transfer effects are not included in the generalized energy balance equations. So if there is a radiative heat transfer happening inside that particular system, we need to model it separately and solve for them. Like pre-existing ones in the energy balance equations are for conduction heat transfer and convective heat transfer. So options are 1 and 2 only. Option B is the right answer. Now we'll go to question 8. Okay, question 7. Okay. Question 7. Advective term includes velocity and take care of the convective heat transfer. Constant property form for the energy conservation equation, rho Cp dou T by dou T. Rho Cp del dot mu T ut is equal to K del square T plus mu phi V. So this is including the conduction part and this is including the convective part. So how the fluid heat is transferred because of the conduction is accounted over here, whereas how the heat is transferring because of the fluid flow, that is accounted here. We have the U term to account the fluid flow motion and T term to account the temperature variation. So fluid convective heat transfer and conductive heat transfer are included in the energy conservation equation. This is a constant property form of the energy equation. So meaning like density is kept constant, Cp is like he const like the amount of heat produced per kg of mass. So this is again constant property for the energy conservation equation takes this particular form. So that's it. So here what do we mean is, which of the following is already included in the energy equation that we solve along with the Navier-Stokes equations for flows with heat transfer and therefore do not require further modeling? So answer is option 1 and 2, that is given from option B, because what we have seen from the original constant property form of the energy conservation equation is that we included the convective part here and we have included the conductive part here. What does convective part mean? The heat transfer due to the flow of the fluid, and conductive part is like how heat is transferred from one atom to another or something, like one particle to another, which is given from this. So now we will go to question 8. In question 8, it is asked that well posedness of an initial value problem means. First one, having the guarantee of a solution. Option 2, it is having a unique solution. Option 3, it is having a solution that is responsive to changes in initial and boundary conditions. Okay. When we are dealing with the like system of equations, we will be using some initial values and solving for and getting the further values. So what does that initial value problem means? Like we all not initial value problems. What is the well posedness of an initial value problems? So for generally when there is a safety solutions, we would be having, if we would be having the governing equations. So the governing equations would again include continuity equation, momentum conservation equations, and energy balance equations and species conservation equations if reactions are considered. So all these are partial differential equations, and therefore like what we do use the discretization and use convert it into algebraic equations. So at that time, like we all use the term like well posedness of the problem. So what does it mean is that like initial value problem. So what it means that it should have the guarantee that it is having a solution, and that solution should be a unique solution, and having a solution that is responsive to changes in initial and boundary conditions. So that solution type should be very responsive. Like if the initial condition is changed, that solution should also be changing. If the boundary condition is changing, that solution should also be changing. So the rate at which it is changing should be very fast. So that is given by all three statements are true. So statement 1 having the guarantee of a solution, that is a true statement. And second one having a unique solution, that again is true. And option 3 it is having a solution that is responsive to changes in initial and boundary conditions. So if we are denoting well posedness of an initial value problem, we need to have all these three criteria. So we'll see the options first. Option A it is 1 and 3. Option Option B it is 2 and 3. Option C it is 1, 2 and 3. Option D none of the above. So answer to this particular problem is option C 1, 2 and 3. So well posedness of an initial value problem means it should have the guarantee of a solution. It should be having a unique solution. So because when we are solving it, why do we need to have this criteria and all? Because we need to know that we would be getting a solution for that, and we would be getting a unique solution. Solution should be real. Like we cannot be having too many solutions as well. Yeah, too many solutions, and that solution in turn should be responsive to the changes in the initial and the boundary conditions. So like at time t is equal to 0, we would be giving out some conditions. For example, let us take a rod and heat it at one end. So initially at temperature at t is equal to 0, when I am starting to heat, the temperature at the other end of the rod might be 0, because at t is equal to 0 only I am lighting the rod. I mean I am lighting a candle and keeping it near the rod. So temperature at the other end would be 0. And if suddenly the condition is changed such that the candle is heated some time prior and it is kept, so that time the temperature at would not be 0, because I am changing the initial condition, and or else I can say that I am heating it to another level, like temperature would be different. So if those changes are made in the initial and boundary conditions, what should be happening, the solution should also be changing fast, and it should be accounting those effects as well. So option C is the right answer, that is 1, 2 and 3. We'll go to question 9. In question 9, it is mentioned that boundary conditions over the entire boundary may not be needed for what type of problem? Option A, it is parabolic. Option B, it is elliptic. Option C, it is hyperbolic. Option D, none of the above. So actually, as I mentioned before, we will be having the governing equations in CFD, and these governing equations are in a partial differential equations. So what we should be knowing is the how to solve these partial differential equations. Before that, we need to identify which class or what is the class, like we should be knowing the class of the partial differential equations. So for that purpose, partial differential equation is divided into three types: A, B and C, and also again one mixed type is there. The classification of PDE is based on mathematical ones. So like each property, like I mean each class, like parabolic, elliptic and hyperbolic would be different one. They would be requiring certain type of boundary conditions for that specific problem. So boundary conditions over the entire boundary may not be needed for what type of problem. So what is given that boundary condition over the entire boundary may not be, like it is mentioned that boundary conditions over the entire boundary is not needed for actually none of the hyperbolic. Okay, what happens is that in parabolic equation, we'll be using the boundary conditions to around the point. Like we'll be seeing further about this in the we'll see about this more in the further slides. And so boundary conditions over the entire boundary may not be needed for it is hyperbolic. So first we'll see what these equations are and why it is not required. Hyperbolic equations, actually this is the hyperbolic equation. So basically when we are dividing the partial differential equations, we are going into three: parabolic, hyperbolic and elliptic. So parabolic hyperbolic equations would be having two characteristic curves, and parabolic would be having one characteristic curves, and elliptic would not be having. So this is the hyperbolic equation. The how we are getting, we are just writing the equation in the original form and getting the coefficient, and we know that b square minus 4ac, and like if it is greater than 0, or if it is equal to 0, or if it is less than 0. If it is greater than 0, it is hyperbolic. If it is equal to 0, it is elliptic, and if it is equal to 0, it is parabolic. So hyperbolic equation. So this is the if let us consider this is the domain. So what happens is that like let us take a point P. So let us take a point P. If there is some disturbance in this particular point, so that particular disturbance is felt over this particular region. So this is known as region of influence. So region 1 is influenced by the point P. And if we extend this particular curve from backwards, we will be getting the domain of dependence. So the value at P, initial data along y axis upon which P depends. So the value at P would be depending on this particular domain, and if there is any disturbance at this point, it would be felt in this particular region. So this is known as region of influence, and this is known as region of dependence. So this is the marching problem. So for example, if from this particular point, if we know, we will be getting this, and from this particular value, if we know, we will be getting the values at this. So this is the initial data along y upon which p depends. So the only value at this particular point is known, needs to be known, and rest we do not require. So this is why we call it as a matching problem, that is one. And here we are not using all the boundary conditions. So like the value at all the boundary is not required for this particular problem. So therefore hyperbolic equation does not require the boundary conditions at all the boundary points. And also what we saw, this is the point P. If there is any disturbance at this point P, it is seen in this particular region. So this particular region is known as region of influence, and this particular point P value is depending on this particular domain. So this is known as domain of dependence. Similarly, if there is a point C, if we consider point C, what this particular region is only affected by the value at point C. This particular region has no effect. So region influenced by point C is this. Whereas again this particular region does not have any influence from this particular point P disturbance. So if there is any disturbance in point P, it is felt over here. Similarly, if there is any disturbance at point C, it is felt over this region. So this is known as region of influence by point C. So like this is covered by the characteristic curve. So that's why we have mentioned that for hyperbolic equations you will be having two characteristic curves, and we do not require the boundary value at all the boundary points. The boundary condition at all the boundary point is not required for the hyperbolic equations. So what is the case for the parabolic equations? For parabolic equation, so this is the initial data line, and we have one characteristic curve that is passing through this particular point. So if there is any disturbance at this particular point, it is felt over this region. So again here it is a marching problem, because from this region we are marching in this particular direction and we know the value. So the region is influenced by point P is this region, and for that we need to know the boundary conditions. So this boundary condition is, if it is known, we can get the disturbance that is felt at point P and in this particular zones. This is again marching problem, because from this particular region we are going marching in this particular direction and we are getting the solutions. So the initial condition is over here, like whatever the initial condition. So initial data line is this and the boundary conditions are these. So from this only we are marching the problem. So boundary conditions is known in the boundaries. So parabolic equation does not fall under that particular case. And the third class is hyperbolic, parabolic and elliptic. So parabolic and hyperbolic equations are marching problems, because from the point, if there is any disturbance at particular point P, we can march forward and see like from till how far the disturbance is traveling. So that is marching problem comes under hyperbolic and parabolic equations. The third class is elliptic equations. Elliptic equation is that here we do not have the characteristic curves. So here the point P, the entire zone is, if there is any disturbance at point P, the entire zone is feeling that disturbance. So what should we know? If there is a single point and the disturbance is felt after that, we can use the marching solutions. But here, since it is disturbance at P is felt in the all zones, as well as the point P is affected because of that, we need to know the values completely. So like it is not a marching problem, but it here it needs to be solved simultaneously. So all those equations needs to be solved simultaneously. So that is known as elliptic equations. So going back into the question, boundary conditions over the entire boundary may not be needed for what type of problem? So it is hyperbolic problem. We do not require the boundary condition over the entire boundary. So because here like single point, its disturbance is felt over here. So this region of influence by point P. So point P is influencing those regions. So we need not know the entire boundary conditions. Now we'll go to question 10. In question 10, it is given that in homogeneous chemical reactions, all the reactants are in same phase. In heterogeneous reactions, at least one of the reactant species is in a different phase. Which of the following statements are necessarily true? So what is given? In homogeneous chemical reactions, all the reactants are in the same phase. Whereas, because what we call homogeneous reaction, like if all the reactants are in the same phase. In heterogeneous reactions, at least one would be in a different species. One species would be in a different phase. So which of the following statements is true? Option 1, all catalytic reactions are heterogeneous. Option 2, all electrochemical reactions are heterogeneous. Option 3, all reactions involving gaseous reactants are homogeneous. Option A, that is 1 and 2 only. Option B, it is 1 and 3 only. Option C, it is 2 and 3 only. Option D, it is none of the three. So here it is mentioned that homogeneous reactions, all reactants are in the same phase. In heterogeneous reactions, at least one of the reactant species are in a different phase. So all catalytic reactions, first statement it is mentioning that all catalytic reactions are heterogeneous. It is false, because it can even be homogeneous. Similar is the case for second statement, that is mentioning all electrochemical reactions are heterogeneous, which is again false, because it can be homogeneous too. Third one is all reactions involving gaseous reactants are homogeneous. It is again not the case, because gas can react with solids or liquids depending on the particular reaction. So answer to this particular problem is option D, none of the three. Yeah, answer is option D, none of the three. We'll go to question 11. Okay, before going to question 11, we'll just take a 5 minutes break. Now the time is 4 o'clock. We'll be joining back by 4:05. Thank you. Can be neglected in formulating the problem. Momentum conservation equation, energy conservation equation, mass conservation equation, and option D, it is none of the above. So answer is option D, because which we cannot neglect any conservation equations while formulating the problem, because momentum conservation equation needs to be known and energy conservation equation needs to be known as well, and mass conservation equation needs to be known as well. And so answer to this particular problem is none of the above. Which of the conservation equations can be neglected in formulating the problem? That is none of the above. We'll go to question 12. In question 12, it is asked that which of the following is a typical fluid flow boundary condition. So uniform velocity at inlet, option 2, it is uniform velocity outlet, zero shear stress at wall. So typical fluid flow boundary condition is velocity flow at inlet, because we would be normally mentioning velocity is inlet is something like when fluid is flowing from this particular inlet and reaching the outlet, what we would be mentioning is velocity is uh, some 1 meter per second or something. Like uniform velocity at inlet is a commonly found fluid flow boundary conditions. So which of the following is a typical fluid flow boundary condition? Is option 1, that is uniform velocity at inlet, that is 1 only. Option B, up 2 only. Option C, it is 1 and 2. Option D, it is 1 and 3. So answer is uniform velocity at inlet is the normal conditions, because we cannot predict the outlet velocity, because only thing we know is we are passing the inlet fluid at this particular condition, but we do not know at what condition it would be coming out from the outlet. So that velocity we would not be knowing, that is not a known thing. And zero shear stress at walls, that would also be, we cannot say for all the fluid flow boundary conditions. So it is not typical fluid flow boundary condition is uniform velocity at inlet. Option A is the right answer. We'll go to question 13. In question 13, it is mentioned that diffusivity of a gas species depends on which of the following? Temperature, pressure, concentration. Option A, 1 only. Option B, 1 and 2 only. Option C, it is all three. Option D, independent of all three. So what is asked? Diffusivity of a gas species is depends on which of the following? Temperature, pressure and concentration. So it is Diffusivity is a measure of the diffusion, that is the rate at which the particles can spread in the system. So it would be depending on the temperature of the system, yes, because temperature would be making out how far it can, how easily it can spread. So temperature is, it is depending, and pressure, because pressure also would be influencing the diffusivity, and concentration again depends. Like again it will depend on concentration. So for example, when we are dipping something, like taking a bowl of water and we are putting some amount of dye. So if the temperature is high, in the diffusivity, like how far it diffuses would be different, and if the pressure, atmospheric pressure is different, it would again be like how fast it is diffusing, it would be influenced by that. And again concentration, if the water is already mixed with so much dye, the future incoming of the dye would be a bit difficult. So concentration is also playing a role. So mostly it would be all three. Diffusivity is depending on temperature, pressure and concentration is the right answer. Option C is the right answer. Now we'll go to question 14. In question 14, it is asked that the truncation error in a finite difference expansion is given by minus dou square u by dou x square at ij into del x by 2 minus dou cube u by dou x cube ij del x cube by 6. So what is the order of accuracy of the finite difference equation? Option A 1, option B 2, option C -2, option D -1. So what is in question 4? It is given that truncation error in a finite difference expansion is given by this. So this is not an expansion. So we are using finite difference approximation to convert from the partial differential equations. So there would be, if you remember, the truncation error term would be there. So from the, which we are neglecting in the equation. So if the truncation error is of the form this, that is dou square u by dou x square at I comma j into del x by 2 minus dou cube u by dou x cube at I comma j into del x cube by 6. So what is the order of accuracy of the finite difference equation? So if you remember in last class also we saw the order of accuracy of the finite difference equation would depend on the truncation error. The highest power of the thing in the truncation error would give out the order of the accuracy of the system. So here highest power of delta x is 1. So order of accuracy for this particular equation is 1, because we have neglected the terms starting from delta x. So the order of accuracy is like the not highest. The minimum delta x power in the truncation error term gives out the order of accuracy. So delta x here is of the power of 1. So answer is 1. Option A is the right answer. The truncation error in a finite difference expansion is given by this. So what is the order of accuracy? So the order of accuracy depends on the power or minimum power of the delta x in the present in the truncation error. So here it is 1. So answer is option A 1. So for example, Taylor series expansion gives okay. Okay, 1 second, just give me a minute. Taylor series equation. So for forward expansion f of x plus delta x, we write it as f of x at x plus dou f by dou x at x into delta x plus dou square f by dou x square at x into delta x square by 2 factorial, and it keeps on going. So for forward difference approach, what we do, dou f by dou x at x is equal to f of x plus delta x minus f of x divided by delta x. So this would be the case, and we would be using this all the other terms would be neglected because we are dividing by delta x the whole equation. This delta x square by 2 would become delta x by 2, because what are we doing here, dou f by dou x we have kept, and we have taken this f of x to the other side. So f of x plus delta x minus f of x, and we have divided the whole equation by delta x. So it is f of x plus delta x minus f of x by delta x is the forward difference formula for dou f by dou x at x. But what terms we have neglected? We have neglected these terms. So delta x square by 2 divided by delta x. So it becomes delta x by 2. So higher the power is 1. So we say the equation is of the order of 1. Similarly, for the Taylor's equation, Taylor series, if we go backward, that is f of x minus delta x, it is given by f of x at x minus dou f by dou x at x into delta x plus dou square f by dou x square by x delta x square by 2 factorial, and it keeps on going. So here it is sign is different from what is appeared in the forward difference formula. So if we write this particular equation in the backward difference approach, we get the dou f by dou x is equal to f of x minus f of x by minus delta x. So we are taking this term to the other side, and we are getting the equation as f of x minus f of x minus delta x by delta x plus order of delta x, because again we have divided the whole term equation by delta x and we have neglected all other terms. So it is the power to this particular term is delta x to the power of 1. So order of accuracy is 1. This is for the forward difference and the backward difference approach. But for central difference approach, if you remember the formula, it comes out as f of x plus delta x minus f of x minus delta x divided by 2 times of delta x, and we have neglected all the other terms starting from the delta x square. So here central difference formula is of the order of accuracy of 2. So it is more accurate than the first order and the second order difference approach, because imagine we are using the 3 points, like we are using f of x plus delta x, f of x minus delta x. So our accuracy is obviously improved, which whereas the case with forward difference and backward difference was we were using only 2 points, the f of x point and f of x plus delta x point, or f of x minus delta x point. So it is order of accuracy is 1 there, order of accuracy is 2 over here. We'll go to question 15. Just a minute, someone is... Yeah. So order of accuracy is also improved over here. So that was what asked in question 14. That what is order of accuracy over here, because we are taking the power of this particular term, that is the smallest power of delta x over here, the order of accuracy is 1. So now we'll go to question 15. Question 15, it is mentioned that find dou u by dou r at point 1 using the forward difference method. So u1 is 0 meter per second, u2 is 5 meter per seconds, and we need to find dou u by dou r at point 1 using the forward difference approach. So what is, if we use the forward difference approach, what would be the value for dou u by dou r? It is like u2 minus u1 divided by delta r. So it is 5 minus 0 divided by 0.5. So here we need to take into account the units as well. So here it is meter per second and here it is centimeter. So accordingly we should check. So dou u by dou r at point 1 using forward difference approach is option A 1000, option B it is 100, option C it is 500, Option D, it is 5000. So answer to this particular problem is option A, 1000, because dou u by dou r by using forward difference approach. So the point is this. This is the first point, that is u1 is here given, dou u by dou r we need to calculate. So at for 1.1 this is 0.2. So for forward difference approach, what we do, we take the next point, that is f of x plus delta x minus f of x divided by delta x. So for getting the value as dou f by dou x at x. So here we need to take u2 minus u1 divided by delta r. Here it is r. So here it is given as dou u by dou r is 5 minus 0 and divided by 0.5. Since it is centimeter, we are calculating this as 10 power minus 2, not 10 minus 2. So on further calculation, we get the value as 1000. 5 divided by 0.5, it would be 10 into again 10 power 2, it would be 1000. So 1000 is the right answer. Now we'll go to question 16. In question 16, it is asked that Lack's theorem states that convergence is assured for well-posed linear initial value problems. Option B, stability is assured for well-posed linear initial value problems. Option C, consistency and stability are sufficient for convergence for a well-posed linear initial value problem. Option D, none of the above. So answer to this is option C. So what is Lack's theorem? Lack's theorem is stating some criteria for getting the convergence. So option A, it is convergence is assured for well-posed linear initial value problems. It does not, Lack's theorem does not state that. And option B, stability is assured for well-posed linear initial value problem. Again, it is false statement according to Lack's theorem. And option C, it is that consistency and stability are sufficient for convergence for a well-posed linear initial value problems. So in order to get the convergence, we need to have a consistency and stability in the system, so that we can say that if it is consistent and if it is stable, we can get a convergent solution. So therefore, for well-posed linear initial value problems, we need to have the consistency and stability as the criteria so that we can assure for the convergence. So option C is the right answer. So Lack's equivalence theorem says that a finite difference approximation for a properly posed partial differential equation satisfying consistency. What does consistency mean over here? Truncation error would be approaching 0 when time step and mesh size goes to 0. Like if the time step is very small and mesh size is very small, so the information from one thing to other would be like information passing is very like in the it is very like all the information is completely transferred because time step is very small and mesh size is very small. For example, like if this is the system, like we can say that, like let us divide into two. It is divided into three in the vertical direction, whereas it is like here the mesh is so refined. So we can say that from this point to this point, the information passing is like complete. So than this, like here the information might be lost over here, whereas the loss of information is very minimal here. So the finite difference approximation for a properly posed partial differential equation satisfying consistency. What does consistency mean here? Consistency is stating that truncation error is approaching 0 when time step sizes and mesh size goes to 0. That is, it is becoming very less. And stability, meaning that error goes on diminishing from time step to time step, possesses necessary and sufficient conditions for convergence. So what does stability state? That stability as the time step is increasing from one time to another time step, as it keeps on increasing, if the error keeps on reducing, we can say the system is stable. If error keeps on increasing, the system is not stable and we would not be getting a convergent solution. If the error builds up at one point, the solution would be diverged. So stability is also a sufficient condition. So consistency and stability. So meaning that truncation error is reducing one side, and as we approach one time to another, the error on the whole is reducing. Therefore, if the consistency and stability criteria are achieved, we can say that the convergence condition is satisfied. The convergence is satisfied when the consistency and stability are sufficient. Like option C is the right answer. Therefore, consistency and stability are sufficient for convergence for a well-posed linear initial value problem. So option C is the right answer. We'll go to question 17. In question 17, for the expansion given by equation A to be convergent, which of the following condition needs to be satisfied? So there is an equation A. For it to be convergent, which of the following condition needs to be satisfied? So A equation is this: f at x plus delta x is equal to given by f of x plus a df by dx plus b d square f by dx square plus c d cube f by dx square dx cube plus d d power 4 f by dx power 4, and it keeps on increasing. For it to be convergent, which of the following condition needs to be satisfied? So we can say that from the Lax theorem, for it to be convergent, we need to satisfy consistency and stability. For consistency to be there, we need the truncation error to approach 0, and meaning that the mesh size and convergent truncation error should approach 0 when the mesh size and the time step is small, and stability when the time step, as time step keeps on increasing, the error keeps on reducing. So when does this happen? We need to have a small delta x. So this is true, we need to have a small delta x, so the loss of information would be less. So we can say the convergent would be there, and f of f to be continuous. So this equation should be continuous, otherwise we cannot differentiate it. So it is, if it is not continuous, we cannot say the solution is expansion given by this would be converging. And since if it is to be continuous, it should be differentiable as well. So all three conditions need to be satisfied. So looking at the options, option A 1 is sufficient, option B 2 is sufficient, option C 3 alone is sufficient, option D all three are necessary. So according to what we require for convergent, we need to have stability, we need to have consistency. For that, we need to have the mesh size small, and we need the system to be continuous and differentiable. So we need all three are necessary. So answer to this particular problem is option D is the right answer, where all three are necessary. Answer is option D. We'll go to question 18. In question 18, it is given that consider the equation dou u by dou y at I comma j is equal to ui comma j minus ui comma j minus 1 by delta y. What is this? This is a backward difference formula, because here we can say that I comma j is the point, but here we are using I comma j and I comma j minus 1. So this is the Taylor series expansion. This is obtained from the Taylor series expansion for the backward difference approach, formulated using the Taylor series expansion. Find the type of equation. So option A first order forward difference, option B first order rearward difference, option C second order forward difference, option D it is second order rearward difference. So rearward difference is nothing but backward difference. So initially we identify the system as backward difference because it is using I comma j point and I comma j minus 1 point. So it is using the concerned point and one point behind it. So it is a backward difference formula. So we need to now identify whether it is a first order or second order. When we go back, this is for the backward, because we identified it as backward difference, we can see that it is a first order. How it is first order? Because we are using f of x minus delta x is equal to f of x at x minus dou f by dou x into a delta x. So we are neglecting all these terms. So after that, what we are doing, we are interchanging the equations, and we are taking this term to the other side and this term to the other side, and then dividing the whole equation by delta x. On dividing whole equation by delta x, this particular term reduces to delta x by 2. So what is the power of this? Power of this would be at that stage, that would become 1. So order of accuracy is 1. So it is a first order backward difference formula. So it is a first order rearward difference formula. So this equation is the of the types first order rearward difference. Answer to this particular problem is option B. Now we'll go to question 9. Consider the following expansion of function f about point I. So the expansion is as this: f of x plus delta x is equal to f of x plus a df by dx plus b d square f by dx square plus c d cube f by dx cube plus d power 4 f by dx power 4 plus this. So consider the following expansion, and value of b in equation A is 2 factorial. Option B 1 by 2 factorial. Option C it is 1 by 4. Option D it is none of the above. So what is the answer? If we using expansion about Taylor series, what we will be getting: f of x plus delta x is equal to f of x plus df by dx into delta x by 2 factorial plus d square f by dx square, sorry, f of x plus df by dx into delta x plus d square f by dx square is into delta x square by 2 factorial. So value of b in equation A is 1 by 2 factorial would be coming. In addition to that, we would be getting delta x square as well. So that is missing in this particular equation. So the value of b in equation A is 1 by 2 factorial into delta x square. So since it is option A, it is 2 factorial, it is wrong. Option B, it is 1 by 2 factorial, it is wrong. Option C, it is 1 by 4, again wrong. Option D, none of the above is the right answer, because d square f by dx square into delta x square by 2 factorial. So delta x square is missing in this particular equation. So answer is none of the above. Now we'll go to question 20. This is the last problem for this session. So in question 20, it is asked that which of these diagrams represent the central difference approximation of dou u by dou x. So option A it is, we have 4 diagrams and we are asked to find which of the diagrams represents the central difference approximation of dou u by dou x. So for that we'll go back to the Taylor series equations which we have written. So this is the central difference formula. So dou u by dou x, in order to get that at x point, what we need u at x plus delta x and u at x minus delta x divided by 2 times of delta x. So since it is of the second order accuracy, so we need 2 points, one ahead point and one behind point. So in question 20, what is asked for at I, if here it is utilizing only this particular point which is false. Again, if we look at option B, it is utilizing only this particular point, again it is wrong. Option C, it is utilizing only the forward point, again it is wrong. Wrong in the sense it is not suitable for the central difference approximation that we are dealing with. So for central difference approximation of dou u by dou x, it would be u at x plus delta x minus u at x minus delta x divided by 2 times of delta x. So it is like ui minus 1 minus ui plus 1 minus ui minus 1 divided by 2 times of delta x. So this is the formula. So we would be requiring ui plus 1 and ui minus 1. So this option D is the option D is the correct answer, which is stating that ui plus 1 and ui minus 1 is involved in the procedure. So which of these diagrams represents the central difference approximation of dou u by dou x is that ui minus 1 and ui plus 1 are required. So answer is option D. So thank you. Any questions? Before that, just give me 2 minutes. I'll be like coming back, and then we can discuss if there are any doubts. Like I have a doubt in one of my questions. Actually, I am new to this NPTEL online course. So for a final exam, what type of Like it depends on, it was computer based question, sorry, computer based exam, that is based MCQ type. It is a computer based exam actually.
Oh, for this course, ma'am?
Yes.
Okay, ma'am. Because I am new to this course actually, so
Okay.
that's it. First time learning in this portal, ma'am. So that's
Mm.
my doubt.
Like to my knowledge, it is computer based. If there is any change, I'll know. I'll let you know in the next week, because from what I saw, it was computer based exam only.
Okay, ma'am. Okay,
Yeah.
okay, ma'am.
Okay. Now just give me 2 minutes. I have a doubt in one question. I'll just check and come. Actually, if there are any doubts, please let me know. Apart from that one particular question alone, which I will post the correct answer when I am uploading the PDF, because I'm not very sure about that answer regarding that this problem. So answer is given as C, but I am not very sure. So this alone I will upload it the answer in the PDF. So other than that, if there are any doubts, please let me know. We can solve the problems. Like I can clear any doubts. So that's all for this week's problems. So now if you have any doubts, we can discuss, and I'll post the question 9 answer properly when I'm uploading the notes, and also when I'm putting the video, I'll put it in the description for the correct and like for a correct explanation for question 9. So other than that, if there is any doubt, please let me know. Yeah. Yeah, thank you. If there are no doubts, we can log off. Like I'll wait 2 more minutes and then we can log off. Thank you. Thank you very much for this week. We will see again next week. Yeah, thank you. I'm just logging off. Thank you.